All right, so this problem deals with a student in an elevator and the motion and forces that sort of result. So we're going to start off with the free body diagram, and then we're going to derive an expression, and we're going to connect that expression to a graph that we have about the forces and the acceleration. So the free body diagram is the first part that's really critical. We have a dot representing the student, and we have to draw what forces exist. Well, he's standing on a platform scale, and he's got mass, and that's really it. So there's the weight up, and there's a normal force, right? That's the ground supporting him. The force of the scale would be another way to label that, anything kind of like that. We aren't told anything about the motion, so we don't know which vector might be longer if they're the same length, so we don't know anything with that. All we know is those are only two forces. There's nothing to making them move side to side. Alright, so part B, we have to take that free body diagram and sort of figure out an expression for the reading on the scale. That's the normal force. And that's Newton's laws, right? The net vertical force equals the mass times the acceleration. Right? And we're not going to say the acceleration equals 0 because we're told that our expression for the normal force or the scale's reading should be in terms of the acceleration. Right? So we'll just leave it like that for now. So upward is positive, so we have a positive normal force there, and a negative weight, which is mg equals ma. And all we need to do is solve for n, right? Once you've done the free body diagram correctly and written Newton's laws, it's pretty fast algebra. And I factor out the m just to make it look a bit nicer. You don't necessarily have to do that. That's it for part B, right? The normal force, or the reading on the scale, is m times the quantity g plus a. Right? So now part C, we have a graph. And we want to sort of use this result, right? We derived this for a reason. We want to use that result to answer the questions in part C. So we want to know what time interval is the force exerted by the scale a maximum. So that takes, we want this to be as big as possible. This is fixed. So we want A to be as big as possible, right? The biggest A will give us the biggest N. So we look at the graph, and that happens between 12 and 16 seconds, right? Largest N means largest A, and on the graph, largest A is 12 seconds to 16 seconds, right? And that's it. That's all it is, right? If we've done the expression correctly in B, part C1 is pretty straightforward. And then it says calculate the magnitude of that force. Well, now we just plug in numbers. Right? We know what the acceleration is 1 meter per second squared. So n equals m 45 g 9.8 plus what the reading on the graph is, plus 1. Or hang on. Sorry, I misread that as 1.2. Right? So we plug all those numbers into your calculator, and you should get 500 newtons. Right? And finally, we go back to the graph and we answer the question, when is the speed constant? This is just a kinematics question, right? Speed constant is A equals 0. So when is the acceleration equal to 0? That happens from 7 to 10 seconds, and it happens from 17 to 20 seconds, right? And so both those time frames are when the acceleration is 0, right? That tells us the speed is constant, and that's it.